Hello, this is Alex Lamb. Today I'm here with a special guest, Sherjil Ozair. He is an intern right now at Google Brain, and he's also a PhD student with me at the University of Montreal. Hello, Sherjil.
Hey Alex, thanks for inviting me to your channel.
Cool. Today we're going to be talking about learning to act by predicting the future. So basically, we're going to be going over this paper by Dosovitsky and Koltun from 2017. And this was an oral paper at iClear. And it builds on the earlier work by Michael Jordan and Rumelhart in 1992, supervised learning with a distal teacher. So basically, the setup assumes that you have these two sensory streams. One of them is high dimensional. One of them is low dimensional. So this high dimensional stream is just the raw data, like usually what you think of as like the state and reinforcement learning. So for example, if it's a game, it might just be the images. And the measurement stream is something low dimensional, something that has like a very well-known structure that maybe you want to maximize. So for example, it might be something like health in a game or speed in a racing game. And the structure of the sensory stream and the measurement stream is always assumed to be fixed in this paper. It's not something that's kind of learned or dynamic. Another aspect here is that there's no fixed goals during training. The goals can change during the course of training, and the goals can also be set when running the model. They can be different from what was used during training. And usually the goal is some function of this measurement stream. Now this differs from what you typically do in RL, where you usually optimize for a single scalar reward. Here you can have like multiple types of things in the measurement stream. And the typical RL setup where you just have a scalar reward can make training harder because there are many different factors that could have potentially led to a reward. So you're entirely responsible for doing this credit assignment problem of understanding what part of the state has value. All right, so Sherjil, you said you had a question.
So this would only work if we have access to a measurement stream, which is not really the case for all sorts of tasks, right? For example, if it's just Atari, then sort of the only thing you have is the rewards from the environment. But of course, if you're playing Doom, then you have much more. I mean, depends on the environment, but you have health, you have like the ammos, you have, and so on.
Yeah, so I think that you can just say that your measurement stream is just the reward. So it kind of has that as a special case, but it's more general than that. Like it can perform better if you have more measurements in the stream. Does that make sense?
Yeah, that makes sense. Except when this method is only used for rewards, I guess there won't be much of a difference, or like it might even perform worse than regular RL methods.
Yeah, so the experiments go into that. So they do like an ablation study with that, and I think it can still help even when the measurement is just the reward. But I think a lot of the improvement in some cases comes from having the other measurements.
Okay.
Yeah. All right. So the basic setup here is that they call it the supervised learning to act. And the basic idea is at a given point, you take the input, which I guess we called the sensory stream, and an action. And in general, you try to predict all future measurements conditioned on you taking the action on this step. Then on each step, one would take the action which has the closest to optimal future measurements. And one natural issue here is that there's kind of no obvious decomposition across time, because hypothetically you just have to predict all future measurements. And another kind of weird thing here is that the future measurements depend on the policy that you'll continue to take for the rest of the episode. So if you just predict all future measurements, you potentially don't cover how well you could do if you had a well-selected policy. You define the agent's objective in terms of a function of the vector of future measurements, as well as what they call a goal vector, which is some weighting over the measurements. And in everything in the paper, the goal vector is given, and this overall objective function u is just the dot product of the goal vector with the measurement vector. Just to give like a really simple example of this, if you care about like both health and ammunition, then your goal vector is just 1, 1. And then the measurements would be the actual health value and then the ammo value, which I think is pretty reasonable. And then for the next part of the setup, basically you define a function which predicts the future measurements given the current action, the goals, and all of the previous observations up to the current step. And then the objective is to pick actions which maximize the linear combination between the measurements and the goal vector. So in terms of how to actually train this thing, you'd probably either run full episodes to train, or if you sort of had like an episode that didn't run all the way to cover all of the future measurements, you could just treat those as missing targets, which isn't necessarily that bad. And then the way they actually do train this is they keep training the network with new experiences from this experience replay buffer, which makes it close to on policy. And the agent follows an epsilon greedy policy for exploration. And in the paper, they experiment with using random goals for each episode during training, as well as using a fixed goal vector during training. Now, basically what they found here is that using either a random goal vector or a fixed goal vector, and when I say a random goal vector, I mean it's the same random goal vector for an episode, but it changes from episode to episode. So if your fixed goal vector at train time is the same as the fixed goal vector at test time, that's usually ideal. But if you're going to change the goal vector from train time to test time, it's usually better to randomize it during training, which is basically what you'd expect. But it's nice to have that confirmed.
Right. I have one question.
Yeah.
So in the previous slide,
yeah.
So you say that in the second point, you say new experience from the experience replay buffer. This is close to on policy. Shouldn't it be off policy? Because the experiences are old now, right? And the policy probably has changed since then.
Oh, all I mean is that because the experience replay is from very recent episodes, the policy probably, assuming it doesn't change very quickly, I mean, it's a certain number of gradient descent steps, it's just close to on policy, but I guess it's technically off policy.
Right. Yeah, technically it is off policy, but yeah, I guess I can see what you mean. So you mean like a laggy on policy?
Yeah,
Right.
I mean,
Okay.
you can always make arguments like if your learning rate, is small enough, I guess it becomes arbitrarily close to being on policy.
Right. Okay.
Yeah.
But usually when people use experience replay, they usually think of the algorithm as an off policy algorithm. And
That's
yeah.
interesting.
Okay.
Yeah. Yeah. So basically, first I'm going to start with kind of just like a simplified version of what this architecture could look like. And this is just your measurement prediction module. So first, you have this input, which is just all the previous measurements. So for example, in a video game, it would be like all the previous images and I guess actions and so on. Oh, but actually, I messed that up. That would be all the previous sensations. In the notation here, measurements are like the health and ammo and stuff. So, but anyway, it takes both all the previous measurements and all the previous sensations, and as well as the goal vector, and it produces an output action. And then all of those things, except for the goal vector, are used to predict the future measurements. Let's see, actually.
I don't think it produces a action. Like the output action isn't produced. Yeah, so if you look here, like in the last,
this one?
yeah, so if you look at the second last vector called prediction, the action taken is just selects one of them.
Right.
So this like the so in the so if you look in over here, yeah, there's like expectation and then action.
Yeah.
So this is just referring to the streams. This is the expectation stream and this is the action stream.
Yeah. So I think what it's doing is it produces like a value over baseline for every action, and then the action is selected by like taking the maximum or an epsilon greedy over that. So you're right that the network doesn't like explicitly output an action.
Yeah, I mean, I guess the action is just a discrete action, so it's easy to just take the argmax.
Right.
So, same as in DQN for the Atari DQN.
Right. Yeah. So this is the actual architecture that they describe in the paper. So yeah. So yeah, so the historical data stream and the goals are used to predict a baseline estimated value for each measurement, which is not conditioned on the action. Let's see here.
Yeah, that's the one on the top. So we are predicting the expectation without taking the so it's doing. So it's not conditioning on the action. It's the sort of the expected value over actions, the mean measurement predictions.
Yeah, which I guess kind of makes sense as a way of decomposing it, because like if you're in a certain situation, there's probably a certain there's probably a certain amount of health that you'd expect to have regardless of the action.
Right.
So
So by the way, this is actually, I'm not sure if this paper has cited the Dueling TQN paper, but this idea was first
Yeah,
introduced by, yeah.
Yeah, they cited someone for that, but I didn't pull up the paper.
Okay. Yeah, they have cited dueling network architectures for deep reinforcement learning. So that was the paper which first introduced this idea of predicting an
Having these two
expectation.
streams. What did you say?
So having like two different streams, one which
Yeah.
predicts the expected value and one which predicts the action conditional expected value. So essentially the top stream is just predicting the state value and the bottom is predicting the advantage, like which is essentially QSA minus VS.
Right.
And when you add them together, then you get the action value of the state and the action.
Yeah, so it's interesting. I guess why is fixing that architecture better than just learning it directly with a neural net? Just like having one neural net.
Yeah, I think it's a bit like batch norm, like the idea that so I'm not. I mean, it's just a better prior, as in.
Yeah, because I guess a neural net could learn to do the same thing. But,
oh yeah, I mean, yeah, sure. I mean, like a single stream neural network can also learn to do the same thing. It's just that in this situation, what you're doing is you're saying that you don't need to look at the action to predict some value, and like for as you said, right? So no matter what action you take, your health is probably going to be the same. So in that situation, the neural network can just learn to use the expectation stream, and the action stream would just be zero.
right.
So yeah, I'm not sure if people have done like very thorough theoretical analysis of how this sort of splitting up it does better, but it does seem intuitively it seems so that like you're sort of decomposing the network into two separate things and sort of ensuring that not ensuring but sort of helping them learn two different aspects of the task separately.
Yeah, another interesting aspect of it is that if you imagine that you had like a good number of actions, the expectation scheme or the expectation stream has something like parameter sharing across all of the actions. So it might be the case that, well,
yeah, that's actually true. That's actually true. If you were just predicting for each action, like if you're predicting separately, then there's, I mean, there is some sharing even then, but it's not an explicit sharing. Now it can
be tricky for the neural net to learn to, for example, have the same parameter value across all those positions.
Mm-hmm. Yeah.
Right. Let's see. Yeah, so we talked about this a little bit, but each measurement prediction is normalized to have a zero mean across actions. So basically that ensures that the baseline model, or we call it the expectation stream, is solely responsible for estimating the mean prediction value. And as I said before, the action is selected using epsilon greedy, which means that with a certain probability, the action is selected using the dot product of the goal vector with the predicted measurements. And then, with 1 minus that probability, a random action is selected. So here are some details about how this is actually done in practice in their experiments. So they actually pick an action once every 4 frames, and they repeat that action across the 4 frames. So I think they said that the the frame rate that they run Doom on is I want to say 35 frames per second. So this allows the agent to take like up to 9 distinct actions per second, which is probably still significantly faster than a human. And one thing that I actually thought was pretty interesting is that I think in all of the experiments, they only use 3 time steps for the measurements. So they predict 8 steps in the future, 16 steps in the future, and 32 steps in the future. And if you put those things together, the agent's only goal goes 3.6 seconds into the future.
Right. I mean, actually, what's even more surprising to me is that it's only predicting 3.6 seconds in the future. So,
Yeah.
so it's obviously not doing any long-term planning.
Yeah.
So, like, it's not taking into account anything like if I take an action right now, what's the effect of the action 10 seconds in the future? There's no
Yeah.
such planning.
Right.
But I guess in such a game like in Doom,
Yeah.
things can be a bit very reactive. As in, all you need to do is like optimize your health and your like ammo. Let's say you can just keep jogging and collecting weapons and ammo, and 3.6 seconds is enough to either avoid like someone shooting you or shoot him. Because when you shoot someone, you will get the reward quite like immediately within 3.6 seconds.
Right. And I mean, it's kind of interesting. I don't know to what extent other people have experimented with this, but I am curious about what the effect is of just using measurements that go farther into the future.
So actually, I did email the authors like immediately after the paper came out because I was like surprised by this result, and I
Wow, what a
asked,
plot twist.
yeah, yeah, and I asked them exactly this. I was like, like how come this works? Like, I mean, aren't you doing more than 3.6 seconds? Don't you need it? And they were like, no, I mean, it doesn't help. Like, I mean, as in 3.6 seconds is good enough.
Well, so
So
I'd be curious if it actually hurt or if it just was about the same.
So yeah, I mean, I think so. They're only predicting like 3 time steps, right? Like 8, 16, and 32. You mentioned.
Yeah.
So I guess if you add a fourth for predicting 64 time steps in the future, so
Yeah.
it's just increasing your prediction by 1. Like you now only need to predict one more time step.
No, I don't mean computationally. I mean like is the performance good? Like if you put in a bunch of measurements that go further into the future, it seems like it would increase the variance in like your gradient. So
Yeah, but it would only cause a problem for your later predictions. As in, your later predictions are going to have higher variance, and they're going to have like they're going to be more error prone. But
yeah.
you can have like you so in your goal vector, you can
Yeah.
have a discount factor for those later predictions. You can say that you're going to rely on those later predictions much less than your earlier predictions, and
Yeah.
and 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 you're good then, right? So you could have a discount factor like 0.9, which is actually
Yeah.
pretty myopic.
No. But I feel like that's only going to get you so far. I mean, I'm curious if you use like kind of a reasonable discount factor and you went a bunch of steps into the future, I'd be curious about how much that hurts this model.
Yeah, I mean, so my bet
would be
that it doesn't
that it
hurt the
doesn't
model.
hurt the model.
It just doesn't help.
Yeah.
Yeah, I'm curious about that. So that would be a good time to segue into me describing what the actual experiments are. So they considered 4 basic tasks within this Doom first-person shooter environment. So the first 2 tasks called D1 and D2. So D1 involves running around and picking up health packs. So I don't think that requires you to think more than 3.6 seconds into the future. And the second task is, or D2, is about running around and trying to get health packs while avoiding poison packs. And in both of these cases, the only measurements they consider are health. So actually, for both of these tasks, if you just look at the structure of the measurements and the rewards, they're the same. They're both just that health scalar, which is something you kind of talked about before. Now, the D3 and D4 tasks both involve combat, and there they have 3 measurements: health, ammunition, and kills. They call kills frags for some reason. And the only difference, in my understanding, between D3 and D4 is that D3 is kind of in a simple environment, and D4 is in more of like a maze with more like obstacles and stuff. And the actions on each time step are discrete, and there are 256 actions which result from various combinations of movement in different directions, jumping, shooting. Does that make sense?
Mm-hmm. Yeah.
Yeah, so let's go over results. So here you can see these 4, I guess, training curves for these different tasks. So,
Right.
So let's see. So it's kind of interesting. They compare against the asynchronous actor critic, the A3C, which is in green, deep Q networks in blue, and something called DSR. I actually don't know what DSR is.
Oh, do you know what the full form is? Okay, it's deep successor representations by it's a paper by Tejas Kulkarni.
Okay.
Yeah, I think it's a somewhat like the sort of the problem with the model is that it's computationally very expensive.
Yeah.
And that's why if you notice, they only do the experiments on the first task, and they only show the results to like the 10 million steps.
I see.
So yeah, I think it's essentially a comparison between DQN and A3C and this paper.
Yeah. So let's see. So on D1, so oh, by the way, they call their model a DFP, or direct forward prediction. So on task one, it converges more slowly than A3C, but it basically gets to the same point eventually.
Right.
On this, yeah.
And DQN like starts off well, and then I mean, I guess it's just unstable, right? Like after 20 million steps, it's like sort of very close to the optima, and then just sort of goes back. But I don't think we should consider that. I think it's like an instability thing. I mean, instability thing. So like your learning rate or whatever might be off at that point.
Yeah, I don't want to get sidetracked too much, but I wonder if these baseline results were ran by the authors of this paper, or if they're copied from another paper.
Oh no, it's this paper, because this is a very new task, and
oh
yeah.
I mean, do you think like these models are like being well tuned and all that stuff?
Yeah, that's a good question. I mean, with DQN and A3C and in general any RL algorithm, I think this is important because they do have to be tuned properly. Like I mean, A3C especially, and even DQN, they have the hyperparameters have to be correctly set. Using a hyperparameter sweep,
Yeah,
and so I think. The most fair comparison is only when you compare with another paper
right.
which has done the hyperparameter sweeps. So I think it's not completely. I mean, there is some information content here, which is that they did try. It does work for one of the tasks, and for the other tasks, it's like slightly suboptimal. There's some
Yeah,
information content, but we can't like. I mean, I don't think you can say with 100 like with certainty that DFP is better than DQN and A3C because someone might come along, use better hyperparameters and use some tricks to
yeah,
make it work better, and
yeah.
that's completely possible.
Now in the author's defense, they also report that it did well in a contest where there were other bots for Dune, and I don't know if A3C, for example, was among the bots. I, I guess the answer is yes, but I don't actually know.
Yeah, I actually don't know either. I mean, there were there were some submissions by by RL folks. I mean, not
Yeah,
really from DeepMind, but there was like student submissions, uh, and people did try like such algorithms, but with like a lot of reward hacking, like
okay.
just to make it work. Yeah. So
Yeah, but
yeah.
that's still good if they performed well in this contest. Um, but I guess one thing that's kind of striking to me here is like the results seem pretty good on the basic task, and it looks like they get some improvement on the second task. But on the third and fourth, these battle tasks, it has a really big improvement. And I think there's pretty good evidence in the paper that the reason why it gets bigger improvement on these tasks is because the D3 and D4 tasks are the only tasks where you have multiple measurements in your
Right.
measurement stream. It's I guess health, ammunition, and kills. So it's a more radical departure from the RL setting.
Right. And also the rewards are more sparse in those settings because you
Yeah,
really have to kill them, and then
yeah,
only you get a reward. And like so you have to aim and do all those things. But in the first two tasks, you just have to sort of like a random policy is going to get some positive reward.
yeah,
So, but that may not be true in D3 and D4. So I think that may be made the difference.
yeah. Do you have any other thoughts here?
I mean, we can talk like some like high level stuff, as in, but later. I mean, do you have any other slides?
Yeah, yeah.
Okay, open questions.
Not so much. So now we're going to switch to something that's a little bit more of, I guess, like an open discussion of various issues that I wrote down.
Right.
So the first thing is, how is this different from the typical reinforcement learning? And to me, it seems like it seems like it has a somewhat immature notion of time. And I mean, just practically in that it only looks a few seconds into the future, but also in that it seems like with temporal difference learning, you have some. Let's see, how do I want to put this? You have some ability to scale to much longer time steps.
Right. I see what you mean now. Like you also mentioned it earlier, like as in like the time
Yeah,
issue, right? So you're saying with temporal difference learning, it handles time very well because it sort of allows you to do really long-term learning. Like it doesn't matter whether you're like whether something is going to be relevant 30 time steps in the future or 100 time steps in the future. Like it's a general RL algorithm, and here you sort of forcing, like you're forcing your horizon to be 32 steps.
Yeah. Now, let's see. Earlier, one point that I made when I was talking about this is if you know that in the distant future, what happens is not really dependent on the current action, you want the selection of the action to not depend on that as much. But it actually seems like here you probably could achieve that because when you have one of the measurements coming out and it's not really dependent on the current action, it seems like the model could learn just to have that value only depend on the expectation stream and not depend on the action at all.
I see. Yeah, so you're saying by decomposing the measurements in time, where like the model can actually learn that taking an action now might give me some measurements in this future, but not in this future, which is something regular reinforcement learning sort of conflates, as in because you just add up all the returns, right? So like a reward at time step 10 versus 20 there's not much difference between them because you're just adding them together.
Yeah.
Right.
Well, so one thing that could be kind of interesting here is if you wanted to consider way more time steps, maybe there's some way that you could make it easy for the model to say something like, okay, if I've already decided that 10 seconds into the future doesn't really depend on the current action that I'm taking, maybe it's like a pretty reasonable prior that all of the time steps after 10 seconds in the future also don't depend on the current action that I'm taking. And maybe there's some way to parameterize it so that you kind of have that prior. Does that make sense?
I see. Yeah, I mean, that makes sense.
So like rather than saying like this is a parameter for 1 second, this is a parameter for 2 seconds, this is a parameter for 3 seconds, maybe say like this is a parameter for 1 second and later, this is a parameter for 2 seconds and later. I don't know, but
yeah, like so more explicitly, so explicitly specifying both the measurement and the time. Like I think right now it's just predicting measurements for each time step in the future, like whatever the offsets are.
I mean, right now they do only. My understanding is they only consider the 3 offsets together.
Yeah. So one thing I'd like to point out is that this work seems very novel, and it is actually very novel in the sense that it combines a lot of good ideas and gets very good results. But as the paper also mentions, it's there's another paper called Universal Value Function Approximation.
Okay.
Which so the core idea there is that you don't just the goal is part of your input. Like so the value function takes both the state and the action and the goal as input.
So the goal in this context, the goal is like a function that maps from the state to the reward.
In this context, yes. And in the universal value function approximation context, the goal is just a goal state.
Okay.
And there's also a recent paper called Hindsight Experience Replay, which sort of builds on top of the universal value function approximation paper. Like these are the idea of like having goal conditional like learning is like what was known, and the advantage of such goal conditional learning is that it allows you to have more data essentially. Like maybe the test goal is is that you have to optimize, let's say, frags, like kills. But
Yeah.
that's a very hard task, and that's a task which has very sparse rewards.
Yeah.
So if you just force your model to learn with that setting, then it might just not learn, because there's not enough, like because it's a very sparse reward setting. So what you do is you make it easier by giving easier goals, such as, hey, just increase your ammo, or increase your make sure that your health is maximized. So these are easier goals to solve, and so at least your model is learning something. At least the first few layers are learning good features about this game environment, and then you could sort of add in these harder goals, such as increasing kills. So then at least your first few layers would have good features to train from. So
Right.
so this idea is used both in UVFAs and hindsight experience replay. Um, Another thing to point out here is that in some sense, and this is also mentioned in the paper, so I'm not saying that they're being sneaky about it, but in
Yeah.
some sense, this is just Monte Carlo estimation of rewards. So of rewards or returns,
Yeah.
except you sort of saying that you only care about uh, like 3.6 seconds. So you're not doing a full return. You just like summing over like rewards till like a certain time. The very novel thing, in my opinion, here is the
Yeah.
idea of predicting multiple measurements instead
Yeah.
of a single scalar reward. And this idea has also, like, recently people have picked up on this idea. There's a paper by Microsoft Maluba,
Yeah.
and they solve Pac-Man using such a reward decomposition, and
Yeah.
like and training like separate value functions for different rewards, because that's a it's a much easier sort of task to learn different types of reward. So one of the value functions could just focus on not dying. Another value function can just focus on collecting rewards. So
Yeah.
and then you eventually combine them together using some sort of a goal vector or something. So I think this idea has like is like according to my knowledge, which is not very uh,
Yeah.
this is like something novel that this paper brought out.
Yeah. But maybe there's a smarter way of putting this multiple measurement notion in the typical RL context. But it seems like you could do something where you have like you just have three Bellman equations for three different rewards, and you just share the parameters between, like, say,
Right, but the typical RL setting doesn't really like allow three different rewards. I mean, like it's pretty, like, if you listen to like a David Silver lecture on this, like um he's pretty adamant that it has to be one scalar reward. Like, I mean, it's somewhat central to the idea of reinforcement learning that you're optimizing one reward. And where this philosophy comes from is the fact that no one can actually optimize multiple rewards, because eventually you'll have some preference order, and you can add them together using weights to make it one scalar,
yeah,
and then optimize that. Is just like, so from a theoretical point of view,
yeah,
one scalar reward is the most, like, is very general. It's just that from a learning point of view, and from a function approximation,
yeah.
and from a generalization point of view, it makes more sense to have multiple rewards.
Right, but
Yeah.
what I was saying is just like what if you literally just say like, oh, I have three different Bellman equations, so you have three different value functions, but I'll have them share most of the parameters. So maybe
Hmm.
you get that advantage from a learning point of view, but I don't think it changes the theory at all.
Yeah.
Um,
Yeah, that's actually like a decent idea. I don't think people have done this. I mean, apart from, like, I mean, the Microsoft Maluba paper, they sort of did very similar to like, so they assume that there is I mean, they don't assume, they just sort of decompose the reward, like sort of themselves, using
Yeah.
some, yeah, it's like it's a like engineered feature. You can think of it like that. And then they solve each problem separately and then combine it together.
Right.
So yeah, that would be one. I mean, yeah. So like this idea can, like, you can use this idea in RL as well. Like, yeah.
Right.
So another thing I wanted to mention was another recent paper by DeepMind called Distributional Perspective in Reinforcement Learning.
Yeah.
So the similarity, sort of the one dimension where these two papers are related,
Yeah.
is the idea that multiple constraints on your functional approximation is
Yeah.
a good idea. So over here, by using multiple measurements as opposed to just one scalar, you're setting more constraints or sort of getting more signal for your function approximation. And so the function approximation is learning much better. And in distributional perspectives,
Is it that they don't just have to estimate a mean, but they also have to estimate like a variance?
so
Critic?
it's not just the variance, it's the full distribution.
Right.
So
Right.
yeah, so in like they actually have like 51 atoms. So like it's so imagine like a discrete distribution,
like a multinomial. Yeah.
yeah. So instead of, so the mean, using just the mean Bellman error, you just have one constraint, and if you have like a distribution over 51 possible values, then you have 51 constraints. So that allows you to, like, it's like more signal to your function approximator. Yeah. So like I just wanted to mention that paper, and it's also a very good paper, I think.
Yeah. Cool. Oh, so another question I had is this method, I guess, learning to act by predicting the future, is it better than doing reinforcement learning, but just kind of having auxiliary targets, for example, on your critic?
In some sense, is the same thing, right? It's essentially auxiliary targets. Like,
well, wait a second. So I'm not totally sure that it's the same thing, because when I think about auxiliary targets, I think like, okay, it's just kind of like a side output, for example, in your value function, but it's not actually literally used in the selection of actions. But here, the dot product of the predicted measurements and the goal vector is also used to pick actions.
So here's the thing, though, right? Yeah. Your goal vector might be a one-hot vector. It might just be like, for example, in the competition, the only thing you're supposed to be optimizing is the number of kills. Like there's no prize for optimizing your ammo. It's just a good side goal. It's a good, like, yeah, not even a goal. It's just like a good sort of side target. So that's my point. So by like one way to think of it, like, because yeah, I mean the reward is just literally just the number of kills, and you've added all these auxiliary targets just to make your training easier, and sure, you have this goal vector thing, so that you're optimizing over them as well during training only, and when at test time you're just optimizing for one of the targets. So in some sense it is auxiliary targets, because like so by auxiliary targets, I guess you're referring to the Unreal paper by DeepMind.
Oh, naturally.
Okay, yeah. So there, yeah, you have like other targets, but it just doesn't make sense to be optimizing them in any way. You're just sort of regressing and like you using it to sort of learn features. And I think a very similar thing is happening here, which is that you're optimizing for ammo and whatever, and you're using it to just learn features, because it's an easier task to optimize for ammo. And so I think it's in the same domain, and I wouldn't really say one is better than the other. It's just, yeah.
I think you actually you could maybe do like an interesting ablation experiment with this. I don't remember if it's in the paper, but you could do something where you learn your network using all of the measurements, but when you pick the action, you only use one of the measurements. For example, the reward type thing. So it would like explicitly tell you
I
whether
see.
picking the action is kind of what matters, or if it's just helpful because it helps you to learn features. I could actually believe that it helps you a lot in picking the action. For example, if you have that game where you're in the battle, you're kind of running around shooting. I think they're monsters in Doom. If you can pick the action to like not get hit or something, that probably helps you to do like more intelligent exploration than the default like epsilon greedy.
Right. Yeah, yeah, definitely. So, like trying to optimize your ammo, for instance, is a very good
Yeah.
exploration policy. At least you're like moving around and doing something useful.
Yeah.
And yeah, so I mean, so yeah, I guess that's one way where it is better if you
Yeah.
remove that aspect. Then, but even in Unreal, you are optimizing for like so the pixel control part of
Yeah.
Unreal optimizes for like changes in pixel, like I mean in pixel values, so
Yeah.
some function of that. So there you are sort of like, I mean, this is like it's behaving like an exploration policy there. So I think these two papers are very related, and like it's sort of yeah, think they share a lot of sort of insights, I
What's
think.
the other paper again?
Unreal,
Okay.
yeah.
Oh yeah. So my next open question is how could you do like sensible off policy learning in this framework?
Um,
So I guess
yeah.
what I'm used to in reinforcement learning is when you have the Bellman equation, you can do importance sampling with off policy.
Wait, so if you just one step Q learning is an
Yeah.
off policy algorithm. So it doesn't require any importance sampling or anything. It's just like the classic Q learning is off policy. Um,
Well, so
yeah.
hold on a second. We might be talking about different things here. What I mean is like, is there some way that you could have data that's drawn off policy and have like unbiased estimates of the gradient that you would get if you were training on policy? Does that make sense?
Um, yeah, yeah, yes and no. I mean,
Okay.
so in Q learning, you actually do that, right? You sample data of like you sample off policy data, and the and the Q function you're training is very different. Like so the policy that the Q function uh, is evaluating is a much better policy, and the data you're using to train it from is coming from a very inferior policy. It might even be a random policy.
Oh,
So
you
so
mean
so
the epsilon greedy policy?
um so yeah, the epsilon greedy policy is used. So it's an epsilon greedy policy of a old Q function, right?
Okay.
So
Oh,
let's
yeah,
say you just,
yeah,
yeah. So let's say you just sample a Q function and then you use epsilon greedy on that Q function.
yeah.
It's yeah, it's essentially a random policy. And if your epsilon value is close to 1, you're essentially just sampling random actions.
Yeah.
But this data is still useful to train any Q function. Like your Q function might be very close to the optimal Q function, and data might like the random data might still be useful.
Yeah.
Uh, so so Q learning is off policy. Over here, I think this is not off, like this model is not really off policy, even though they're using an experience replay and sort of like incorrectly using an experience replay to train this thing. because it's predicting multiple steps in the future.
Yeah.
And yeah.
So to be honest, I think I might be thinking of something a little bit different. What I mean is, like, let's say you just trained this model, you have the model now, and
Okay.
I tell you, like, okay, I'm going to run the agent on another policy, or like I tell you, like, okay, the agent, like, I'm going to let you pick the next action, and then all of the later actions are going to be picked under this other policy that I'll tell you about. Now, how can you use this algorithm to correctly pick the next action? Does that make sense?
I see. Okay. Yeah, that makes much more sense. Um, yeah, I guess you could do something like importance sampling. I can't really do math like
Live.
live, but I guess you should be able to do importance sampling with, you could just like, I mean, so there's a mean squared error, and then you would just multiply the importance sampling there. Except, yeah.
But right here, I mean, it seems like it would be tricky to put into this model because it seems like the knowledge about or what's learned in this prediction network kind of has the future policy baked into it.
Right. Yeah. But like most Q functions have that. Like, I mean, there is an implicit contract that I'm going to take this action, and then in the future I'm going to use this policy.
Yeah.
So like, yeah. Um. So what you're saying is something like there is an implicit policy that the function predictor, whatever the function approximator is, like the predictor, it has some implicit policy, but what you're saying is, let's say something like I'm going to use some other policy,
Yeah,
and
yeah.
then train. I think we're talking about very similar things. Like Q learning is also very similar, and I think if people are interested in like sort of learning more about off policy, there's this very good paper called Safe and Efficient Off Policy Learning. It's by
That's the retrace paper.
yeah, that's the retrace paper, and it's a very, like, I mean, it explains the idea very well, and like it has a lot of good references and so on. So yeah, I mean, it talks about importance sampling and sort of sets, like, I mean, compares like 4 different algorithms and how they're related to each other and stuff. Yeah, but I mean, I guess I think it should be possible, but I'm not sure.
Yeah. Right. Oh, so another question that I had is how is this related to conditional batch norm? And to me, it seems like this baseline network that goes in a separate stream seems a bit like conditional batch norm.
Yeah, I mean, one thing I'd like to say here
I'm just going to
is,
go back to it in the slides. Yeah.
okay.
Yeah.
One big difference between batch norm in general and the sort of dueling architecture is
Yeah.
that the dueling architecture is completely encapsulated, like outside, like, so like what, it's just a different network design which has
Yeah.
no side effects. Like, I mean, you don't need to worry about it outside the network. So which is something that like which is not in batch norm. You do have to worry about it, right? It's not just a simple change in architecture. It's not just, instead of using, it's not just resnets where you just change it and forget about it, because now you have to maintain these means and variances, and it's different for the training distribution and different for the test distribution. So I think batch norm has like some side effects, and
Yeah.
it sort of and it mixes the optimizer and the model together, and all these problems. So this does not have all those issues. It has some like similar insights in that like it's just sort of saying that the expectation can be independently computed. So like this different, like if things can be decoupled into different things, like I mean different submodules of the network, then that's a good thing. And that's what batch norm does. It like sort of makes these layers as independent as possible. And that's what we're seeing here. But yeah, do you have any like do you have anything to say here?
Well, so maybe it's a little closer to like layer normalization than batch normalization.
Yeah, I guess in the sense that layer norm, I guess, does not have the problem, right? The training, you don't
Yeah,
have to maintain any statistics.
yeah,
Yeah, I mean, there's actually a recent paper.
yeah,
It was just mentioned on Twitter. I don't even remember the name. What they do is like each like neuron. So odd neurons have a regular ReLU layer, like
yeah,
ReLU activation, and even neurons have a inverse ReLU, as in it's it has a slope of 1 in the negative side of things, and it's just 0 in the positive axis. So
yeah.
if x is less than 0, y equals x, and if x is greater than 0, y is equal to 0. So something like that. And that also ensures that like the mean activation is 0. So
Oh, so are you talk? Is this the thing from the shattered gradients? Like if resnets are the answer, what's the question?
oh, no, this is a very, like, I just saw this yesterday. No,
Oh,
that's not the
what
thing.
is it again?
It's you have like, so odd neurons have a ReLU activation, and even neurons have a negative ReLU activation in some sense.
Yeah,
So that like in a very weird way, it ensures that the mean activation is 0.
right.
But yeah, I mean, I don't know. I mean, I probably shouldn't even have mentioned that paper. I mean,
Okay.
yeah, we can probably cut it out.
Nah, and you know what? We're even we're gonna even keep in the part where you said we should cut it out. Make it real. Oh, anyway, so this is my last open question. So one thing that's interesting to me in the setup here is, it decomposes the state into these two different things: sensations, which are the raw observations, like the images or the audio, and then these measurements are higher level things that we care about. And at least to me, as I'm mostly a generative models researcher, measurements sound kind of like latent variables.
Yeah, definitely. I mean, you can probably imagine training like an encoder which just predicts all these measurements, and it should be completely possible. You just need like some supervised data, or unsupervised. Like you could just train a variational autoencoder and try to get these measurements. Mm-hmm.
So it's kind of interesting. I feel like there's a few things you can say about this, though. So, um, in this Doom example, the things that you had were kills, health, and ammunition as the measurements. Now, one property that these things have is they're kind of directional in the sense that, like, if I'm going up to, like, 10 kills, uh, that's sort of, what do I want to say? If I want to go up to 20 kills, I have to go to the intermediate values of like 10 kills, then 11 kills, then 12 kills.
Mm-hmm. Yeah.
They sort of have this continuity between
Oh,
each other.
okay. I see. I see. Yeah. It's
But if
it's
I have,
essentially it's essentially a real number.
yeah,
Yeah.
but if I had like a normal, like latent variable, like that I just learned from a generative model, and I just keep like shrinking or increasing the value of that dimension, um, does that necessarily mean anything?
Isn't it the same thing? I mean, even in variational autoencoders, at least the continuous type, like they are also directional, right? Like increasing them causes, uh, yeah. I mean, it doesn't like
It should,
skip over, right? I mean,
yeah.
like the
Well,
latent variables model things like thickness of the digit, which
yeah.
is very similar to
Yeah, well, I
yeah.
guess one thing more formally you could say is that because the prior in the latent space assumes that the different dimensions are independent, like marginally independent,
Mhm.
uh, then by changing the value of one dimension, that shouldn't tell you anything about the values for the other dimensions. So it seems like you should get something out of changing the value of the dimension. But I think there's something more here that I'm getting at, which is that when you think about time, to get from one value, like a health of 100 to a health of 50, it's like I have to pass between these intermediate health values in order, if that makes sense.
Yeah. Okay. Yeah. Which you do not need, which you need not do in if you're
Yeah,
in variational autoencoder, because you can just set it to 50. Is that what you're trying to get at? Okay,
yeah. I think that's what I'm getting at.
I see. Yeah, I mean, like yeah, you can only go so far. Is what you're saying. You can't just have a policy which allows you to go from 50 to 100 directly. Actually, you know what? I mean, like you can have health packs,
Oh
which
yeah,
are like yeah. So that's okay. So it's not completely true then, right? Because
so let's work through this idea more concretely. So let's say you have some data where someone was playing this Doom game like really well, like an expert, and you collect all of all these images together, and let's say you train like a good generative model of it, like you train like Ali or a VAE or something, and you have these latent variables. Now, let's say you use this model, learning to act by predicting the future, and you say that your measurements are the latent variables of that generative model. Do you see what I'm saying?
yeah, yeah.
What would the model learn to do?
Right. I feel like it makes some sense because the variational autoencoder is essentially like the latent variables are essentially encompassing the whole like sort of state space. Like everything you have seen in the state space, you're sort of trying to summarize that in the latent variables extents,
Yeah,
and then when you have a goal vector, which
yeah,
it's going to try to like increase the extent of like you're trying to you're going to try to change the z values to their extreme points, and
yeah,
and so that's a very directional exploration policy as opposed to something like epsilon greedy, which is which is a random walk. So you sort of explicitly whatever variation you see in the world, you're
yeah.
trying to increase the variation even more.
By the
And
way, do you know off the top of your head, if you took something like a variational autoencoder and you took a certain dimension and you just kept increasing the value, my guess, I haven't actually tried it. My guess is that it would eventually just break the model, like it would go to nans or something. I mean, just because of the way neural nets work. So
mhm,
maybe when you frame the objective function here, rather than making it the dot product of a goal vector with the measurements, maybe what you would do is you make it like the square loss or
yeah,
something, where like the goal is to get to a particular measurement.
yeah, yeah,
Yeah,
that makes sense, except
yeah,
I don't know. I mean, I think goal vector also makes some sense because, then you're sort of trying to increase the reach of your model. Like, because
Right, but like as a hypothetical, let's
I
say
mean,
like it just goes to black or something if the first z dimension gets too big, like it just breaks the decoder or something. Like
yeah.
it's gonna keep pushing up the objective just by getting in the black corner or something. Does
Oh,
that
okay. I see. I see. I mean, in that case, you can just say that this particular episode was not very useful. But I mean, like the problem with just so imagine just sampling one of the z vectors and just saying just reach here. So the problem with this is when you sample a z, it's going to be you're going to sample a high probability z vector, right? And so you already know how to go there, and so what this may make you do is just travel around the sort of the central area of your environment, but
Yeah,
but actually what you want to do is travel to regions which you haven't seen. You want to go to the low probability value. So maybe that's the thing, right? Maybe you could just sample a low probability z value and then try to go there.
but there's another thing with time here, which is that if the models, like if we did the thing I suggested earlier, where you say, I'm going to do the square loss between the goal vector and the measurement vector as my objective, um, it's kind of weird because all the model wants to do in time is it wants to get to this one kind of state and then just stay in that state. Whereas if you look at the stuff in this paper, it's like, um, you know, even when you're at like 10 kills, you want to keep doing things and keep acting to get to like 11 kills, 12 kills, 13 kills. Does that make sense?
Yeah.
Um,
It's trying to optimize something, and over here it is trying to optimize something, but it's trying to like stay in some state.
yeah. So this is kind of an abstract comment, but like if you had like a temporal generative model, and then you had like latent variables that didn't just describe like a single point in time, but described like change over time. Like if you did the same thing where it tried to get to a certain latent variable, that would describe like having a certain dynamics in time,
Mhm.
like certain types of change that you would try to get to, rather than just getting to one type of latent variable. Does
Yeah.
that make sense?
Yeah. Except I don't know of such a model. I mean, like a temporal VAE. I mean, okay, there's some naive instantiations you can do, which is like run an RNN encoder over like a video and just get one Z value out of it.
Right.
But it's sort of it's sort of a, I mean, the side point is like I think we really don't have good temporal generative models.
Yeah, there's another thought. Yeah, that's probably true. There's another thought that I have here, which is that in the setup I described earlier, it's like you assume that you have a bunch of recorded states, and then you can build like this generative model and latent variable model on those states, and then you can train this kind of model which learns to act. But it might also be interesting to consider the case where you're trying to learn the two models together, like you only have the states that you've seen so far to train
Yeah,
the model.
yeah, definitely. I mean that's what I was thinking of. Like, I mean, of like you train both of these together.
Yeah.
One thing is that this is only a good exploration model, right? I mean, it's
Well,
or maybe, yeah, maybe you could add the reward as well. Yeah, I mean,
hold on a second. I think it's downplaying a little bit to say it's just exploration. Because if you had a model and it knew how to get to a state characterized by certain latent variables, like that could be a very interesting model to have.
Oh, yeah.
Like,
Yeah,
yeah.
my bad. Like, I mean, and actually you can, if you had rewards as well, you could just add the reward as an extra latent variable, and then you could optimize for all of them together. And even if you have sparse rewards, you could just work with your latent variables, and then when you do observe some rewards, you could optimize for them. So
Yeah.
yeah, I mean, I agree it's downplaying a bit. I mean, this is actually a decent model. uh, do you know about um, do you know the independently controllable features paper by our
Yeah.
advisor?
Yeah. I'm actually kind of interested in making a video about that. But
Okay.
anyway, what were you going to say?
I mean, I'm just saying, do you know how similar, like, isn't it exactly what we're talking about? It's trying to learn a latent representation of the observations of the states, and then trying to sort of optimize for each of them separately. Like, so, like, I mean, I think in their case, the goal vector is like a one hot vector, where you sort of, you want that you optimize for one of those, like you change one of those latent variables as much as possible, but you don't change the others at all. Just so it's like controllable features, right? Is you want to try learning z values which are independently controllable, such that it's possible to learn a policy which can control them independently.
That doesn't seem like exactly the same idea.
Yeah, I guess I guess this, like, what we are talking about here might be a simpler idea, because it's not trying to do anything like independently controllable. It's just sort of expressing the variations of the environment in terms of latent variables, and then this just trying to optimize them.
Yeah.
Yeah, in some sense, instead of specifying goals like as pixel level goals,
Yeah.
what we're doing is like trying to like learn like, yeah, like trying to represent the states in a much more compact representation, and then specifying the goals in terms of those representations.
Yeah.
Yeah, I actually have a modification. Like, I mean, so in this case, you are learning pixel level decoders, right? You are like you would be learning a decoder which predicts pixels from,
You mean in the hypothetical that I'm discussing?
yeah, like the
Yeah.
unsupervised learning to act by
Yeah.
predicting the
Oh,
future. You are going to learn a generative model, right? Which
yeah.
is,
The pixels thing. Yeah.
which is not the easiest thing to do, and like we haven't really sort of
Yeah.
solved the problem convincingly. I think, I mean, we're making progress, obviously.
That's
But
true. But one thing I'm going to add is for the type of model that I'm describing, the most important property of it is that it learns to have latent variables that describe the world. Uh,
yeah.
and
So,
it could be the case that you have something that's kind of formulated as a generative model, but it kind of emphasizes having like a high level understanding of things in terms of latent variables over having like a pixel level accurate generative model. And you could also
I
have
see.
a way of doing unsupervised learning of latent variables that doesn't involve a generative model.
Yeah, I mean, the latter is actually, I think, a very good goal. Like, I
Yeah,
mean, I'm actually very interested in trying to come up with a very like a good generate. I guess you won't really call it a generative model in this sense.
yeah, but
But
figuring out some kind of space. So learning to have a space where you have
yeah,
a
I
generative
guess you can
model.
call this manifold learning, or representation learning.
Yeah,
So like, so let's, yeah, learning like representation of a high dimensional space, like, or input, without trying to predict it back, like without trying
yeah.
to learn the reverse function. Just learning an encoder without trying to learn the decoder, and without
Not
access to the,
necessarily, because I mean, it's kind of interesting when you think about like like when humans imagine things, you can't really do that. I mean, it's not literally pixel level at humans for humans, but I don't think when you think of something, you think about it at like a literal visual level or a literal auditory level. You have an ability to just generate this higher level representation of something. But it seems tricky to figure out the right way of formulating learning something at a higher level where you're learning the mapping from the lower level to the higher level as well, because
because you could just cheat, right?
you could just multiply it by 0
Yeah,
at the
exactly.
higher level and then say, oh, well, it's really easy to model the higher level now. So it has to be something more than just something that's easy to model at the higher level.
Yeah, so I think that's where temporal comes in. Like if I just give you a static data set of like 50,000 MNIST images, and then I ask you to just learn an encoder without a decoder, I think that's an impossible problem, and as that's a like truly ill-defined problem. And the best you can do is just like learn a zero vector, is a zero encoder. But if I give you a sequence of MNIST images, let's say, like, like the images transitioning into each other or something like that, then there is signal here. Like, I'm not giving you any labels, but the sequence itself is a label. The fact that this digit is following another digit and is followed by another digit, like, there's a smooth transition going on. That's a very solid source of signal. And then it's not really an ill-defined problem, but we haven't really solved this problem. I think there are things like slow feature learning, which tries to solve this problem, but they're not, like the representations, it's just hearsay, but the representations I think turn out to be very impoverished, as in they don't capture everything. And so I think it's an open problem of it's a sort of a very well-defined open problem. Like, how do you learn representations without learning a decoder? And I think this might be the key to unsupervised learning, because because it is really hard to predict these pixels, and like the pixel level representation has a lot of noisy features, like has a lot of noise in it, which is not useful to anyone. Like, I mean, you don't really want, like, you probably don't even remember the color of like a building you pass through every day when you go from home to lab, right? You probably don't know the color, but you know that there is a building. You know what's important about that building, let's say how high that building is, but you don't know.
I do, because all the buildings on our campus are gray.
Okay, maybe the campus, but you, like, what I mean was, I mean, you probably understood it, but there are objects, there are things about certain things, but you only know some features and you don't know the other features. Like, for instance, I'm somewhat colorblind, so I don't remember colors too, because of this thing, because I don't trust colors. So I never remember colors. And like, if you ask me what like, if you like, this is news to me that all the buildings in our campus are gray colored or whatever. I don't even bother. So, but I do remember them. I can even picture them, but I don't know the colors. Like, and I probably don't know a lot of salient features about those buildings. So therefore, I think, like, it's like predicting pixels, like, is really like the wrong thing to do. And it's like 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 a lot of the generative models research community is sort of in this trying to solve this problem, which I think is the wrong direction. And it would be much better if people tried to focus more on like this other problem of learning an encoder without a decoder.
Yeah. So,
but I mean, looking at samples from generative models is a very, like, I mean, you like I guess it's very interesting to do that. So
Yeah,
So
I
I
mean,
think, yeah.
I will add that when I talked to when I interviewed Martin Orzechowski, I did ask him about like what he thought were like the most interesting open research problems in generative models, and he talked about this exact issue. So
I see.
I
So,
think
okay, so people are aware, I guess. Yeah.
yeah, but I think the discussion of it in context of
Reinforcement learning.
actions is also interesting.
Yeah, I think that's what I think. So some people say unsupervised learning hasn't really worked and stuff, and that's true. And I think where unsupervised learning can really work is in the domain of reinforcement learning. I think unsupervised learning alone is not signal enough, and reinforcement learning alone is not signal enough. But the two together have a lot of they sort of they're complementary. So in an MDP, if the only signal you use is the reward, then it's a cherry on the cake problem. But you are getting more signal from the MDP, which is the next state and the state after that. So, and that's a very rich signal, and that is like proper signal. Like it's not just unsupervised. It's not just here's some data. It's information in the sense of this is a state which comes after this other state. So these two together, I think this is this is I think a very promising direction, and uh, this is where both of these sort of subfields of machine learning can now sort of band together and try to beat supervised learning.
Yeah.
These are like some very meta level comments. Do you want to talk about like the model? It's like specifics, any more like specific thing, like about unsupervised learning to act, or
we've probably been going for a while, so it might be good to wrap things up.
okay.
Do you have any like closing comments or anything?
No, I recommend people like check out this paper. I think it's a great paper, and sort of it's very against the grain in reinforcement learning. It's sort of it's a Vladimir Colton's writing style is very, or I guess like Alexei's as well. They're very like, I mean, they write very different from like the typical RL paper from DeepMind or Berkeley or OpenAI. So it was refreshing. And I think like, yeah, I mean, there's been more work around this. Obviously, there's been hindsight experience replay, and also distributional perspective, which I think if people are interested in this paper, they should also read those papers. Yeah. Do you have anything to say?
No.
Okay. All right. Yeah. So yeah, thanks for inviting me again. This was a great, like, I really enjoyed talking to you about this paper and just in general chatting you about research directions.
Yeah. Good to talk to you, Sherjil.
Okay then. All right. Bye.
Bye.